Hey, welcome to The Explainer. Today we're going to crack open a really powerful tool for dealing with uncertainty. It's called a Bayesian network. All right, so to really get this, we're not going to start with some dry definition. Nope, we're going to jump right in with a puzzle.
So picture this. You're trying to figure out the chances of a day off from school. You know that a bunch of things are connected, right? Like humidity, whether it's cloudy, if it's actually raining. They all play a part. So how in the world do you calculate the odds when everything is tangled up like this? Well, that's exactly the kind of puzzle we're going to solve.
First things first, to solve a puzzle like this, we need a map that shows us how all these different things actually influence each other.
And that map? That's really the heart of a Bayesian network. It's just a simple graph that shows you what depends on what. You've got arrows pointing from a cause to an effect. It's super intuitive, and it makes even really complex relationships, well, pretty easy to see at a glance.
Okay, so for our little weather mystery, we're going to start with humidity and clouds. Now, in the language of these networks, we call these parent nodes. Why? Because in our little scenario here, nothing causes them. They're just the independent starting points.
Next up, we add rain. Now, rain is obviously affected by both humidity and clouds, right? So we draw arrows pointing from humidity and clouds to rain. This shows us visually that rain depends on them. Its chances are conditional on what those other two things are doing.
And to finish it off, we've got wet grass and school off. Both of these, you'll notice, depend on one thing: rain. So we draw our last arrows from rain to these two, and there we have it. Our map is complete. The whole web of cause and effect is laid out right in front of us.
Now this map actually highlights something really important. You see, some things, like the school off day, they only depend on one parent. In this case, rain. That's pretty simple. But other things, like rain itself, depend on multiple parents. And that's where it gets interesting. Because to figure out the odds of rain, we have to look at every single possible combination of humidity and cloudiness. Okay, so we've got our map. Now it's time to put some numbers on it. We need to gather our evidence, the probabilities.
So let's start with the basics. These are our first clues, just the general, everyday likelihood of it being humid or cloudy. You can think of these as the base rates for our parent nodes, the ones at the very top of our map.
And here's a super useful fundamental rule of probability. If you know the chance of something happening, you automatically know the chance of it not happening. It's just 1 minus that number. So, like you see here, if the probability of cloudy is 0.6, then the probability of not cloudy is just 1 minus 0.6, which, is 0.4. Easy. Okay, now this is where things get really powerful. We're moving on to what we call conditional probabilities. This is how the network shows us the way probabilities change based on other things. We're not talking about general chances anymore, we're talking about specific conditional ones. It's the exact same logic a doctor uses to figure out what's wrong based on your symptoms, or how your favorite streaming service just knows what movie you want to watch next. So check out this table. This thing holds all the clues for rain. It lays out every single one of the 4 possible combos of its parents, humidity and clouds. So, for example, you can just look it up. If it's not humid, but it is cloudy, boom, there's a 70% or 0.7 probability of rain. All right, let's grab the last set of clues we need for our little investigation. This one's way simpler because it only has that one parent variable. So according to our evidence here, if it's raining, there's a pretty high chance, 0.7, that school will be canceled. But look, even if it's not raining, there's still a small 0.2 chance of a day off. Maybe a pipe burst, who knows? The point is, the network is smart enough to account for that kind of uncertainty too.
Okay, we've got the map, we've got all the clues. It's time to put it all together and finally crack this case.
So how do we get our final answer? It's actually pretty straightforward. We just follow the paths on that dependency map we made, and we multiply the probabilities at each step. We're literally just chaining together every piece of evidence to calculate the odds of that very specific scenario we asked about at the beginning.
Okay, first piece of the puzzle, we need to find the probability of a school day off given that it's raining. Remember, our question assumes it's raining, so we need that specific number. And if we look back at our school off table, we can see that when rain is true, the probability is 0.7. Easy. That's our first number. All right, now let's grab the rest of the numbers we need. So, from our big evidence table, the chance of rain when it's cloudy but not humid, that's 0.7. We also know the base chance of it being cloudy is 0.6. And since we know the chance of it being humid is 0.2, the chance of it not being humid is just 1 minus 0.2, which is 0.8. And just like that, we have all the pieces of our puzzle.
Okay, here we go. We just multiply all those numbers together down the chain. So that's the chance of a day off because it's raining, that's 0.7, times the chance of it raining because it's cloudy and not humid, that's another 0.7, times the base chance of it not being humid, that's 0.8, times the base chance of it being cloudy, which is 0.6. You multiply all that out and you get our final answer, a 23.52% chance of this exact scenario playing out. We did it!
So, we solved our little weather puzzle. But let's zoom out. Why does this way of thinking, this whole method, why does it matter so much?
Well, because this way of thinking is an absolute cornerstone of modern AI and data science. It's the engine behind systems that have to make smart decisions when they don't have all the facts. We're talking about things like medical diagnosis, weighing all the symptoms to find the most likely disease, or spam filters, figuring out the odds an email is junk based on its words, all the way to speech recognition, figuring out what you probably said to your phone.
The truth is, once you start looking for it, you see this stuff everywhere. From your morning coffee routine to global supply chains. The world is basically just one giant Bayesian network, full of these hidden, interconnected causes and effects. And now, you have the key to start seeing it.